Here we go, 4.6 review. Okay, first problem. $1,000 is invested at 3% return rate, compounded monthly. How long will it take for that money to triple? In other words, the amount to go from 1,000 to 3,000. Well, for this problem, we're going to use the compounding formula. And the formula for compound interest is total amount equals principal times 1 plus the rate divided by n, where n is the number of times it's compounded, and that quantity raised to the n times t power. And here, P is 1,000 because that's our principal. The rate is 0.03. N is 12 because it's compounded monthly, 12 times a year. A, you're probably wondering, well, we don't know what A is. But yes, we do, because the problem is how long for 1,000 to triple, meaning A is going to be 3,000. So we do know what A is. It's 3,000. And what we're finding here is T. So we're going to plug all those values in and then solve for T. So we plug the values in, and we get 3,000 equals 1,000 times the quantity 1 plus 0.03 over 12 raised to the 12t power. So this is an exponential equation. We have the quantity raised to an exponent. Our variable is in the exponent. So we want to isolate that quantity. We do that by dividing both sides by 1,000. So that gives you 3 equals 1 plus 0.03 divided by 12 to the 12t power. Now, to get that t as a non-exponent, we take logs of both sides. It doesn't matter whether you use base 10 or the base e logs. I'm going to use the base e logs, ln of both sides. So we take ln of both sides, and now, because of our exponent property, that 12t goes out in front. It's no longer an exponent, which allows us to solve for t. So we get natural log of 3 equals 12t times ln of that quantity. Now we divide both sides by 12 times ln of that quantity, and we get ln of 3 over 12 times ln of that quantity, 1 plus 0.03 over 12 equals t. And now we can use our calculator to evaluate that. And when we do that, we get t equals 36.67 years rounded off, which is approximately 36 2/3 of a year. Okay, in this next problem, a city has a population that grows according to this model. P equals 10,000 times e to the 0.03t power. In how many years will the city have a population of 60,000? So in this case, we just replace P with 60,000, isolate the exponential, then take natural logs of both sides and solve. And we solved problems like this in the previous section, so hopefully you can solve this. Give this one a try on your own. Solve for t, and round off to 2 places. So you should have started out by putting in the 60,000, then dividing both sides by 10,000, giving you the equation 6 equals e to the 0.03t power. So hopefully you have that. If you don't, start from that point and finish this problem. So we take natural logs of both sides, which enables us to move that exponent out front. So we get ln of 6 equals 0.03t times ln of e. Now remember from section 4.4, log base e of e equals 1. So the ln of e disappears. It's just a factor of 1. So we just divide both sides by 0.03, and we get our answer, ln of 6 over 0.03 equals t, which is, it ends up being 59.73 years when you round it off. Okay, the next problem, kind of like number 3. A city with population 20,000 grows exponentially at a rate of 5%. In how many years will the population double? So here I haven't given you a model, but we can come up with a model quick enough. The model for exponential growth from your notes or the book, n as a function of t equals n sub naught e to the kt power, where n sub naught is the initial amount, n as a function of t is the amount at any time t, k is a constant which corresponds to the growth rate, and t is the time periods that also match the growth rate. So k would be growth rate per time period. Well, here t is years, and our growth rate is 0.05. So we've got that. We also know that the city has an initial population of 20,000. So n sub naught is 20,000. And the question is, in how many years will the population double? Well, we would let n of t equals double 20,000. So let n as a function of t equals 40,000. So now we can plug in all the parts of that model with only t that we have to solve for. So see if you can do that. Solve it. The solution is very much like the problem we just did. So pause the video and try this. So after we plug in all the quantities, we get 40,000 equals 20,000 e to the 0.03 t power. Divide both sides by 20,000 and we get 2 equals e to the 0.03 t power. Take natural logs of both sides, which allows you to move that exponent out front like we did in the previous problem. ln of 2 equals 0.03 t, and then we can solve for t by dividing both sides by 0.03. So when we do that calculation, ln of 2 divided by 0.03, plug it in our calculator, we get about 13.86 years rounded off. And I just noticed that I switched the 0.05 into 0.03. I did have the correct final answer. So that was ln of 2 divided by 0.05, not 0.03. Sorry about that. What's interesting here is this not only applies to populations, but it applies to money in a bank earning interest. It's exponential growth, but it's very close to growth that's compounded monthly. If you have $20,000 invested at 5%, in about 14 years, it's going to double in its value. Okay, on to the car value problem. A car sells for $25,000 new. After 3 years, it is worth $18,000. What will it be worth when it's 8 years old? So it's like we have a car that's 3 years old and it's worth $18,000. What's it going to be worth in 5 years from now when it's 8 years old? So to do this, we use that same model. We're assuming exponential decline, and I've actually done some work with this and shown that cars do indeed reduce in value according to this exponential decline model. N as a function of t equals n sub naught, or initial value, times e to the kt power. So we have the n sub naught. It's 25,000. And that's all we have. But we can use the given data to solve for k. We let n as a function of t equal 18,000 and t equal 3, and plug in the n sub naught value. And then we can solve that equation for k to get our growth constant. So when we plug in the values, we get 18,000 equals 25,000 e to the k times 3, or 3k power. And now you can solve that just like you solved the previous equation. So try and solve this for k. So once again, we isolate the exponential, the e to the 3k, dividing both sides by 25,000. So you get 18,000 divided by 25,000 equals e to the 3k, or 18/25. Then you log both sides with natural logs, which allows us to move the exponent out front. So we get ln of 18/25 equals 3k. Then we just have to divide both sides by 3. And when we do that, we take the ln of 18/25 divided by 3, rounded to 4 places, we get negative 0.1095 equals k. What that's telling you is this car is losing about 11% of its value each year. Of course, each year it has less value to lose, so the initial years is where it's really losing its value. That's why they say as soon as you drive it off the lot, it loses so much value. That's true. And once the car is not worth much, 11% isn't that much money. So now we have k, and we can write out a completed model. So our completed model is n as a function of t equals 25,000 e to the negative 0.1095 t. With that model, we then can predict the value at any year, plugging in whatever t value. In this question, we want to know what's the value when t is 8, so we just let t equal 8, plug it in, and calculate the result. And when we do that, 25,000 times e to the negative 0.095 times 8, we get 10,411. If we round that out to the nearest $100, it's $10,400. Okay, we're going to look at number 7 from the homework. The population of fish is given by p as a function of t equals 20,000 over 1 plus 130 e to the negative 0.18 t power. How many fish are there initially? Well, initially means t equals 0. So you just let t equal 0. E to the 0 is going to turn into 1. So you end up with 20,000 over 1 plus 130 times 1. So that one's pretty easy to calculate. How many fish after 1 year? Well, 1 year, oh, and I forgot to indicate from the homework, t is in months. That's important. It's on your homework problem. I was just trying to be a little more brief here because I have lack of room. T is in months after these fish are stocked. So after 1 year, t is not 1, but you just let t equal 12. Now the question people get stuck on is part C. What's the maximum number of fish? Well, the maximum number of fish is when that denominator is as small as it can be. And really what the denominator here is equal to is 1 plus 130 over e to the positive 0.01 t power, because the negative exponent means you invert. Well, as t becomes larger and larger, that power of e gets to be a pretty big number. When t is 10, we have e to the 1.8 power. That's 6, which isn't much. But then when t is 100, it's t to the 18th power, which is 65 million something. When t is 100, that 130 over 65 million something is practically 0. And as t gets bigger and bigger, the closer this fraction gets to 0. if you just plug in t equal 100 or 1,000, you're going to find you have 20,000 over 1, because that fraction is going to go to 0. So your maximum is going to be 20,000. And there I've written it so you can see it was off my board on the bottom. 20,000 over 1 is going to go to 20,000 because that fraction is going to go to 0. So this is what's called the logistics model. And if you were to graph this, you find it has this exponential growth, but then it levels off to this maximum amount, which in this case is 20,000. This is actually the way a flu virus follows if there's no measures to contain the virus. Right now we're dealing with this pandemic where we're trying to stop this type of growth, because this maximum would be our whole population potentially, and we don't want that all at once. So that's why all of this is going on. So we don't really follow this curve. We don't want to follow this curve, but typically for a flu virus, this is the way it grows when no measures are taken.